Hi, this is the first of what I plan to be several videos on Algebra 2 in dialogue with Glenn Coe's McGraw-Hill's 2003 high school textbook on Algebra 2. I'm sure that there have been upgrades to it, but math doesn't change that much, really, over time. Well, this is not exactly, though, in the order that it follows, because I am also a teacher, and I would like to put things in an order that makes better sense to me. So the first video, I want to start with what is actually the second section in the first chapter of this Algebra 2 textbook, and that is to talk about different kinds of numbers. Now, we all grow up with the natural numbers. We have 10 fingers, most of us, 1, 2, 3, 4, the counting numbers. You might call the counting numbers in math are called the natural numbers. Another way to call them are the positive integers. Again, with a lot of math, just don't ask the why question. Well, why are they called integers? Don't ask those kinds of questions. This is why you'll go crazy. In fact, I'm convinced that math is easier than a lot of people make it out to be, because they're asking a why question for which you just don't, one, you either don't need to know why, or two, we don't know why, or maybe it just is. But we start with the counting numbers, 1, 2, 3, 4, 1, 2, 3, 4, whatever language you want to count in. We call these the natural numbers because I was born with these fingers, so it's natural for me to count them that way. They're also the positive integers. Don't ask why, just memorize that the natural numbers, the ones that come with my hands, are the positive integers. And that's what we call them. Of course, the natural numbers go beyond these 10 fingers. I can start counting 11, 12, 13, 14, 15, 16, and on and on. And if I had an infinite amount of time, I could go on to, very, very large numbers counting on my fingers, as long as I stopped and took a little sugar so that I could keep lifting them, because if I didn't eat, of course, never mind. Okay, so the natural numbers, that's the place we all start off with, at least everybody I know. There might be some weird person that jumps straight to complex numbers, but that's not important right now. Okay, so whole numbers. Whole numbers are the natural numbers plus 0. Now, this may seem strange to you, but we don't have any record of people thinking of 0 as a number until the Gupta Empire in India around the time of Christ. And then I believe it came into kind of Europe through the Arabs. There were a lot of Arab thinkers and mathematicians in the early Middle Ages until they were squashed. But anyway, that's not important right now. So 0, the idea of a number that represents nothing, actually is fairly late to the game of human history when you consider how long human history has been going. So the whole numbers are the counting numbers plus 0. 0 plus the positive integers are what we call whole numbers. Now, as you may have learned, you can extend these numbers into what are called negative numbers, or the negative integers. That's why the natural numbers are positive integers. The negative numbers are, at least as I'm talking about them right now, are -1, -2, negative. We could conceivably use our fingers, -1, -2, but negative numbers are really the same as subtracting. So -2 basically means subtract 2. So if you were to go from 0 and subtract 2, you would get to the number we call -2. It's like taking away and rewinding. So that's the integer. So the set of all integers includes 0, all the positive natural numbers, and then a new group that goes also to negative infinity, -1, -2, -3, to negative infinity. You surely learned all that in Algebra 1. Rational numbers. These are not numbers that are very logical and make sense. They wear sensible clothes. They're rational. They're not irrational. They don't, start screaming uncontrollably. These are the rational numbers. That's not what it means. Rational, in this case, means that they can be put in the form of a ratio, a number over a number. Remember, numerator, denominator, with a line in the middle. Rational numbers means that numbers can be put into the form of a fraction. Now, the rational numbers actually include the integers, because 1, the number 1, for example, can be put in the form of a fraction. 1 over 1 is 1. And because the number 1 can be put into the form 1 over 1, it is also a rational number. So you might say that the integers are a subset of the set of rational numbers, and the whole numbers are a subset of the set of integers, and the natural numbers are a subset of the set of whole numbers, which is a subset of the set of integers, which is a subset of the set of rational numbers. And you can have a lovely little chart with circles inside of circles. So the number 300 can be put in the form of a ratio, 300 over 1. See? So 300 is a rational number. Negative 292 can be put in the form of a fraction, negative 292 over 1. So the rational numbers include all of these other numbers that I've mentioned. Okay, irrational numbers. What are irrational numbers? Well, if rational numbers are numbers that can be put in the form of a fraction, irrational numbers are numbers that cannot be put in the form of a fraction. The first one that comes to mind is pi. Pi is 3.1415926535323, and it goes on to infinity. Pi is the ratio of the circumference of a circle to the diameter of a circle. And it's always the same. For any true circle, the ratio is going to be 3.14159 and so on to infinity. Because pi goes on to infinity with no predictable repeat, there's no repeating. So there is a kind of a 0.6666666. That actually can be put into the form of a fraction. That's kind of a 2/3 fraction. And you can have, 0.18. Those can usually, those repeating decimals can be put in the form of a fraction. But something like pi cannot be put in a form of a fraction. It just goes on forever, 3.14159265353. Now, some of you are thinking, well, why do I need to know this? I'm not sure. But it's in the book. I just find it interesting. So just pretend like you're listening to a tape with a song on it you don't like, and just put up with it for a few seconds here. Because it's not hard to understand, right? I mean, you can throw a few brain cells my way, surely. Okay, so other irrational numbers, some square roots are irrational, like the square root of 2. That's the number that if you times it times itself, you get 2. But it goes on forever and ever and ever and ever. The square root of 2, what is it, 1.414, and it goes on, forever. So there are these irrational numbers that they're not repeating, they just go on forever. And they arise in certain circumstances. So where do square roots come from? The Greeks are the ones who first, I think, discovered square roots. Somebody probably had before then, but these are the ones that wrote it down. So like if you have a triangle with a 90-degree angle, then to find the length of these sides, you're going to need to know square roots. And so a lot of math arose in ordinary kinds of conversations. Well, how much rope do I need to go from here to the top of that pole? Well, if I know triangles and the Pythagorean theorem, I can come up with it, but it's going to involve some square roots. Okay, now, from the rational numbers up, everything was a subset of the thing below it. But irrational numbers are now something completely different from rational numbers. So you have rational numbers and you have irrational numbers. These are two completely different sets. There is nothing in the set of irrational numbers that's in the set of rational numbers. So if we take both of those different sets and put them together, we have the set of real numbers. So the set of real numbers includes all rational numbers and it includes all irrational numbers. And there you have it. There is another set that you'll get in Algebra 2, but not today, and that is the set of complex numbers. The set of complex numbers includes real numbers, but it also includes numbers that you need for quantum physics if you want to build a spaceship to go to Alpha Centauri. Complex numbers involve something called the square root of -1. Now, since any number times itself, a negative times a negative is a positive. A negative times a negative is a positive, and a positive times a positive is a positive. So how can you multiply something by itself and get a -1? It's just impossible as far as the world we observe around us. But mathematicians invented something they called I, which stands for the square root of -1. And that enabled them to create a whole nother set, a whole other group of numbers that they're not real numbers. In fact, these complex numbers are sometimes called imaginary numbers. And believe it or not, they actually do become important in quantum mechanics, which has to do with subatomic kinds of math. So they are actually real and not imaginary when you get down to the atom level of things. But you don't need to know any of that today because complex numbers are in a much later chapter in Algebra 2. There you have it. I've overviewed the different groups of numbers as we know them in Section 1-2 of the Glencoe Algebra 2 textbook as of 2003. Now there are some properties that these real numbers have that I thought I would just mention. The first is the property of identity. That is, one thing that is true of all real numbers is that if you add a 0 to it, you still get the same number. Or if you multiply any real number by 1, you still get the same number. You may not know what it's called, the property of identity. You don't have to know what it's called to be able to do it. Any number times 1 stays the same number. Any number plus 0 stays the same number. So notice there is a additive identity and a multiplicative identity principle at work here. Then there's the inverse principle. This is very important in algebra, that you be able to do it whether you know what to call it. So if you add the negative of a number, you get 0. So 1 plus negative 1 is 0. Remember how I said negative 1 was kind of like subtracting 1? 1 minus 1 is 0. Same thing, 1 plus negative 1 is 0. The multiplicative inverse doesn't end up with 0 if a times 1 over a gives 1. And this is very important in algebra, that you be able to apply these to equations to solve for things. So those are the inverse principles of addition and multiplication, respectively. The commutative property is that a plus b equals b plus a. That's the commutative property of addition, that you can change the order that you add things together, but it's still going to end up the same. There's also the commutative property of multiplication, that no matter what order you multiply things in, it's still the same. So if you do a times b or b times a, it equals the same. Again, you don't have to know what that is called to be able to do it, the commutative property. The associative property of addition and also multiplication is that even if you add a plus b first and then add c, or if you add b plus c first and then add a, you're still going to end up with the same sum, or if I had to put the multiplication on here, the same product in multiplication. By the way, in the first section of Glencoe's Algebra 2, they talk about the order that you do things. I thought it would be better to do this video before we did that, but notice that when you mix and match multiplication and addition together, then the order becomes important. So you don't add before you multiply when you have a mixture of addition and multiplication, or division and subtraction. So the associative principle works when you have just addition or when you have just multiplication, if that makes sense. Then the distributive property will end this video, and that is the idea that if you multiply an a times something in parentheses, b plus c, a lot of times the beginning math student will just do ab plus c. That's wrong, wrong, wrong. You have to multiply the a by everything in parentheses. So a times b plus c is ab, and it's ac. It has to the a has to multiply by everything in the parentheses, and that is the distributive property.